In this screencast, we are going to talk about chemical bonds. Now, all chemical structures, including those in skin and hair, are held together by a number of forces, right? And we're going to talk about those different forces. And the first type of force we're going to talk about are really strong bonds like chemical bonds. So in cosmetic products, strong bonds can also be formed between ingredients and can help keep a product stable. And so this is one of the reasons why we're going to investigate these chemical bonds, because we'll refer back to these chemical bonds when we start to talk about the products. Now, when we talk about chemical bonds, just a general definition here is this is the force of attraction between any two atoms in a compound or molecule. There are three basic types of chemical bonds that we're going to talk about. There's ionic, there's covalent, and then there's metallic. Now, given the nature of this course, we are going to talk about ionic and covalent. We do not run into metallic bonds very much in cosmetics, so we're not going to talk about those. So what we're going to do through this screencast is we're going to look at a quick overview of ionic and covalent molecules, and then we're going to focus on ionic for the rest of this screencast, particularly naming them. Then in the next screencast, we'll talk about naming covalent molecules. So for an overview, we need to talk about Lewis theory just a little bit. And this is a picture of a gentleman named Gilbert Lewis. And he's the one that proposed that atoms form chemical bonds by sharing electrons to achieve an octet, right? Or those 8 valence electrons. Now, when he did this, he came up with Lewis symbols to help us visualize this. And this is just a chemical symbol with the valence electrons represented as dots. Okay. Now, when we look at these Lewis symbols, you can see some here. So when we've seen this before, we've got this group with 1 valence electron. That dot is the valence electron, right? So when we have these unpaired dots, a lot of times this is referred to as bonding capacity. It helps us predict how many bonds these elements can make. And then, of course, it helps us with our valence electrons. So our main group elements here, these have the same number of valence electrons and similar bonding capacities. Okay. Now, so for example, we know here that carbon has 4 valence electrons. It has 4 dots here. And if we want to get to 8 electrons surrounding it, then it would want to borrow 4 other valence electrons to get to 8. Okay, so what we find is that some elements want to share to get to 8, and then some elements want to give up or take electrons through chemical reactions to get to 8. Okay, and so ionic compounds, which we've talked about briefly in the previous screencast, these are, right, we have these electrons and they are lost or gained. And it's important to understand the electrons that are lost by a cation are gained by an anion, right? And so we see this in salts. So for example, if you've got sodium chloride, right, we've got sodium, it loses an electron, but in reality what it does is it gives that electron to the chlorine ion, and that forms this positive and negative charge, and these are attracted to each other because just like think of different sides of a magnet where you have a positive side and a negative side, and they're attracted to each other there. And so these are ionic compounds where we've got cations and anions, and we've got these opposite charges that are attracted to each other. Okay, so that's our first type of compound. Our second type of compound that we're going to talk about through the rest of well, in the next screencast, we're going to introduce it here, are molecular compounds, and these are held together by covalent bonds. So and so these molecular compounds a lot of times are just also known as covalent compounds. Sometimes they're referred to as covalent molecules. So you'll hear both of those kind of interchangeably there. So when we talk about this, it's important to talk about covalent bonds. These are bonds that are created by 2 atoms where they share one or more pairs of electrons. And so a really good example of this, for example, is if we form hydrogen gas, which is H2. Hydrogen has 1 electron, and it reacts with a hydrogen with another electron, and when these form H2, one has brought 1 electron, the other has brought the other electron, and now they're sharing those. You can show it like this, but most often we represent this with a line. So that line is a single bond. And so with these covalent bonds, we represent them a lot of times with lines. So if you have a single bond, that's 1 line, and we're sharing 2 electrons. If you have a double bond, that's 2 lines, and we're sharing 4 electrons, like you see here in CO2. And then if we have a triple bond, 1, 2, 3, we are sharing 6 electrons, which you see here in carbon monoxide, 1, 2, 3 there. Okay, so covalent bonds, right, are the sharing of electrons, and there's 3 types that we'll run into: a single, double, or triple bond. So those are our 3 types. In the next screencast, we're going to talk about the molecular compounds or covalent compounds. But for the rest of this screencast, we are going to discuss ionic compounds and how to name them. So in ionic compounds, right, these are generally a metal and a nonmetal. Metals form cations and nonmetals form anions. A lot of times it'll be referred to as a formula unit. And so that's just the smallest electrically neutral unit of an ionic compound. And that is, like, for example, with sodium chloride would just be NaCl, right? And so that's what we would see there with ionic compounds. Now, charges on the ions, depend on the location on the periodic table. So let's look at a periodic table. So for example, everything in group 1 here forms a +1 charge. Everything in group 2 here forms a +2 charge. When we look over here, one of the things that we'll see is that noble gases don't form a charge at all. They don't react. They're very unreactive. But here our halogens will form a -1 charge. Our chalcogens will form a -2 charge, the nonmetals here. And then here in group 5, nitrogen and phosphorus will form a -3. I also want to draw your attention to kind of this area of the periodic table, because these also have only one charge, which is 3, 2, and 1. Now, so we can use the periodic table to help us predict the charges, but it's also important to notice that we can have some atoms that have more than one charge. And so when we have more than one charge, we use a Roman numeral to tell us the charge. Okay, so you use a Roman numeral to tell the charge. When there is more than one. So for example, iron, you can have iron with a 2+ charge. We would show that in the name, right, as iron 2, okay? You can also have iron with a 3+ charge, and we can show that as iron 3. And you're also going to see that written out as iron 2 or iron 3, okay? And so that's what we will see there. Now, let's talk about how we name these ionic compounds. When we name the ionic compounds, these usually consist of a cation, which is usually a metal, and anions, which are usually nonmetals. You put the cation first, and you just give it the element name, right? And that's going to be the thing that's on the periodic table. And then the anion comes next, and instead of using the periodic table name, you're going to drop the ending and add IDE. So instead of chlorine, it would be chloride. Instead of oxygen, it would be oxide, okay? And then the formulas here always have to be neutral. Now, what do I mean by that? Well, if we have magnesium chloride, and we look at the periodic table and we see that magnesium has a +2 charge, and then chlorine has a -1 charge. We have to have as many, the charge on all the chlorines has to cancel out the charge on the magnesium. So magnesium has a +2, so it would need then to be bonded to 2 chlorines so that these charges add up to -2, and we'll cancel out that +2. And so from that we get MgCl2. Now, you can most certainly do it this way, but there's another way that you can do this. When we talk about Mg2+ and Cl-, you can crisscross the charges to make them the number of atoms, and it will work out the same way. MgCl2, right? Where the charge now becomes the number of atoms in both cases. There is a caveat here. So for example, if we were doing magnesium oxide, for example, and we looked and we said, hey, look, magnesium has a +2 charge, oxygen has a -2 charge, and so those will combine in a 1-to-1 ratio to give us magnesium oxide. when we do the crisscross down like that, that gives us Mg2O2. If you can divide these by the same number, then you need to do that and reduce them down to their whole number. So MgO would be a really good example. So these are all examples of how we can go from the name to the chemical formula. And we'll practice this more in class. Now, the other thing to be aware of is when we talk about this are the Roman numerals, like I mentioned. And the Roman numerals stand for the charge. And so I have a Roman here that's charging into battle to help you remember this, right? So that Roman numeral stands for charge, right? And we put that in parentheses when we are doing the naming. This chloride floated over here. I'm going to move it back over here. Okay. So when we look at this, you can have copper 1 chloride or copper 2 chloride. This just means that in this instance, copper has a +1 charge, and in this instance, copper has a +2 charge. Okay. And so, for example, if we were to say, hey, look, we are gonna write the formula of iron 2 chloride, right? We know iron has a +2 charge and chloride has a negative charge. We would crisscross those over and it would be iron Cl2, okay? And that's iron 2 chloride. If we looked at iron 3 chloride, for example, right? That Roman numeral tells us the charge. So it's a Roman numeral of 3, that's a 3+ charge. Chlorine has a -1. We crisscross those over. It ends up being FeCl3. And again, right, we will practice this more in class, but I want us to do a few more practice problems on the next slide. So when we're naming these ionic compounds, right, I want us to practice naming NiCl2, okay? When you approach this, okay, when we're naming these, right, you need to first ask yourself, right, does the metal have more than one charge? Okay. When we look at nickel, right, nickel is not in group 1, 2, or the area that we circled, right, on the periodic table with aluminum or zinc or silver or cadmium, okay? So it will have more than one charge, okay? If the answer here is yes, you need to figure out the charge, okay? And the way that you figure out the charge, right, is you start with the nonmetal, because we are always going to know the charge of the nonmetal. Nonmetals don't have multiple charges. They always have one. So we look at chlorine. We see it's a halogen. So it will always have a -1 charge. Okay, so that means for us then, when we look at this, chlorine, there are 2 of them, and they have a -1 charge. Nickel, over here, there's only 1 of those. Whatever charge nickel has, it has to cancel out that -2 charge. So that means for us then, nickel has to have a +2 charge. So when we write the name of this ionic compound, it's going to be nickel 2 chloride. Okay? Let's do another one. Let's look at MnO2. Okay, and we've got to write the name of this. Now, this is a really good example of where you can pause the screencast and try this problem and then check your work. So if that's something that you want to do, if that's the way that you want to use the screencast, I would really suggest that. If not, that's okay too. So we are going to go through and ask ourselves kind of this series of questions. Can this metal have more than one charge? Is it in group 1 or 2? No. Is it in that kind of area on the periodic table with aluminum, silver, cadmium, and zinc? No. So then manganese here can have more than one charge. So that means we need to start with the oxygen here because it can only have one charge. I look at the periodic table and I see that oxygen is in group 6. I know that group 6 has a -2 charge. Okay? When we look at this negative, there's 2 of them. There's a -2 there. That adds up to -4. When we look at the manganese here, that means it must have a +4 to cancel out that -4. So the answer to this would be manganese 4. The Roman numeral 4 has an I before the 5. Okay, 4 oxide. And so that would be the charge there. We'll practice more of these in class. I'll have some handouts for you to take home. And then, of course, if you want more problems, there are plenty of problems out there on the internet as well. So when we're naming ionic compounds, we have to deal with Roman numerals. Another thing that we have to focus on are polyatomic ions. Now, polyatomic ions, these are just groups of atoms that are nonmetals that have a charge. Now, I am going to give you a list of the ones that you have to memorize. It is not as long as this. Basically, the only thing you can do is memorize these when we use them in names. However, there are some things that can help us with this. One of the things to be familiar with is if you have an oxoanion. Now, oxoanions are just these polyatomic anions that contain oxygen, right? So there's these polyatomic, poly just means many atoms, many atomic atoms, right, with oxygen. And what you're going to see there is that you're going to see several that end in ATE or ITE. And what you're going to notice is that if there's an ITE and an ATE, the ATE will always have one additional oxygen than the ite, okay? So the 8 will have one more oxygen than the ite. And we like to say that it ate an extra oxygen, okay? So for me as a student, right, I memorized all the sulfates and then I just subtracted an oxygen to get to the ite, right? So 8 has one more oxygen than ite. If you're familiar with other prefixes, sometimes this helps, right? Per means one more oxygen. So if we look at the chlorate and we have perchlorate, it's going to have one more oxygen than the 8. Hypo means that you have one less oxygen than the ite. So hypochlorite. So that's some ways that we can use those prefixes to help us memorize that. So let's look at an example here where we have, and we are going to name sodium sulfite. So when we go to name sodium sulfite, we go to our periodic table for sodium. Sodium has a +1 charge. It's in that first column. It can't have multiple charges, right? So that would be sodium. Then we come here to sulfite, and we know because we memorized it, because Dr. Pierce told us to, it's SO3 2-. We crisscross applesauce those down, and we end up with Na2SO3. Okay? Now, there's one other thing that I want to talk to you about, and that is parentheses. If you have more more than one polyatomic ion, you need parentheses. So, for example, right, let's say that I have chromium perchlorate. Okay. And I need to give chromium a Roman numeral, so I'm actually going to give chromium 3. Sorry, I left out the Roman numeral though. Chromium 3 perchlorate. So when we're working here with chromium 3 perchlorate, we know chromium has a 3 plus charge. We've got perchlorate. We know that perchlorate is ClO4 minus. Okay. When we crisscross these across, right, there's one chromium, and because we have more than one polyatomic ion, we put the polyatomic ion in parentheses and then put the number that tells us how many polyatomic ions that we have outside of that. Now, when you're calculating up your number of atoms, you're going to multiply this number by what's inside the parentheses. So we have one chromium, we have 3 total chlorine ions, and 3 times 4, we'd have 12 total oxygen ions. If we just put a 3 next to the oxygen here, that wouldn't communicate the same thing. So we'd get a different number of ions. That's why we use parentheses. We'll work on this more in class. So if you're feeling a little uncertain about it, please don't panic. And as always, I am happy to help in office hours as well. So again, we'll work on this more in class. But if you still feel a little uncertain about it, please, please, please stop by my office.